is to go with computer randomization of what you guys did over hundreds of thousands of trials. So check this out. Let me scroll this down so you can see a little better. How many of you guys had the blue dice? Okay, we had a few groups of blue dice. I'm going to use the blue dice as the example. Now, I put without loss of generality. And I burped. I apologize for that. That means that it doesn't matter what dice we analyze, the result I'm about to see would hold for all of them. Not just blue, they will also hold for orange or yellow or green or red. I just happened to pick the blue one first to build a spreadsheet around. Fair enough? Okay, so we know the average of those dice is 8.166666 and the standard deviation is 2.65. You've forgotten that since Monday, bless you, that's totally fine. There it is. Okay, so far? Now here is what the distribution looked like on Monday. We figured this out. I made you guys figure that curve out. Exactly, very much skewed left. You sat down with the dice, and Riley had that really cool little thing she had figured out with the 1s and the 6 and the cross. And you figured out this is what the graph looked like. Now, what's cool about this is Excel is not figuring it out like you did. All it's doing is it's throwing the dice and keeping track 10,000 at a time. So you see how it's changing a little tiny bit there? It's fluttering around the true values, but it's got so many values that the error becomes negligible. So that's the graph of the distribution of the population through random samples. The problem is that represents 10,000 samples, which generally researchers get 1. You don't get 10,000, you get 1. So you get 1 of these. And that's what you guys were doing on Monday. This is what you guys did on Monday. Now, this isn't exactly what your curve looked like when you put your curves on the board Monday. And the only reason it didn't was because, where were the blue groups again? Yeah, you guys had 75 total trials, correct? 25, 25, 25. This has, I believe, 1,000 trials. So look what's happening. Now, what do you notice about the curve? It's a beautiful bell, isn't it? It's a beautiful bell. Can you tell where the average of the distribution is, roughly? What point of the bell? 18. Exactly, it's going to be roughly where the highest point of the bell is, right? Now, why does this make us happy?
Reasons?
Why does it make us happy to know that the average of the population is at the highest point of that bell?
We're close to the same as the average.
Exactly. You're not privy to the average of a population, usually. If I ask what the effect this little pill is going to have on an ADHD kid's attention span, you don't know what the true average effect is in the general population, do you? So what do? You give that pill and a placebo to whom? To a sample of them, whether it's 10,000, whether it's 4,000, whether it's 400, whoever you can get. You give it to a sample of them, and you check the results of that sample, and you graph that sample. What this tells us is our samples do a pretty good job of targeting where the actual population average is, even if we can't get the population average. Isn't that badass? That's kind of badass, I think. Maybe a little bit. Maybe a little bit. Now the problem is, of course, this is 10,000 samples. What if you were this one out here? Well, that kind of sucks, doesn't it? Because you missed poorly. Remember, we've talked about this before. 95% of the data is within 2 standard deviations. Well, that means 5% are outside. It's not likely, but it's possible that you get out into the wings, correct? Well, that's a bit of a problem now, isn't it? How can we fix that? Oh. No, we think this medicine works, Alicia. We've spent tens of thousands of dollars on this medicine, and we think it works, and we're not going to do this illegitimately. What's a legitimate way to try to catch the average more? It's something Taryn said about 6 weeks ago. Say that again. More trials. Now, I never would have asked you guys to do this in class, but what happens if you sample 9 at a time instead of 4 at a time? So this, instead of, you guys roll the dice 4 times, right? And then averaged 4. This is rolling the dice 9 times and averaging 9. What do you notice about the results in the curve? What do you notice? Oh, Sandy. It did this. What else did it do? You guys did, yes. So remember how in the last curve I got down here? I could have gotten down here. Look what I can't do anymore. It's no longer getting down here. It's getting too hard to land in the tail. Now the average is still right about here, isn't it? The curve is still humped right about in here. But the tails are disappearing, which means more of the data is landing closer to the average. How can we get it even closer?
More trials.
More trials. Here's 16. Here's 16.
What about 30?
I skipped over 30.
Oh.
I went, there's 16. Notice, it's getting tighter. In case you're having a hard time seeing it getting tighter, look at the percentages over here. The highest point on this curve is up at 0.3 or 30% right now. Originally, back here, the highest point was at 0.14, which means we're shoving those in a lot more tightly now, aren't we? So there's 16. How about 25? Shrink it down so you can see it better. Fewer bars, yes, fewer bars. High point now is between 0.3, 0.35, or 0.4. You see that? How about 100? Now, look at that high bar, 0.6 now. Now, many people look at this one. I realize that many people look at this one and they say, I don't see a bell curve anymore. Because it's condensed so far down. So what I did was I added a page to this one, and I only focused on where the data is actually popping up. So notice how this one goes from 2 up to 12. You can't get all those anymore. So what I did was I only went from 7 up to, it looks like 9 or 9.5. So in other words, this distribution is the same set of bars you were just looking at, except I gave it, the bars are now narrower. Which means, so what shape is in there? Once again, it's a bell. So this bell curve exists right here in these 3 or 4 bars. It's just these are half a unit wide, and those were 1/10 of a unit wide. So you got 5 times as many bars. Sandy, go.
You're doing this too on the frequency side. You're over 50% too, which is.
You noticed that, didn't you?
Yeah.
You noticed that, sister. Good for you.
Because
Look.
that way you do more trials too, is to get it
Wow.
there. It's over
Yes.
50%.
You want to get that as high as you can't get it to 100.
Yeah.
There's always going to be the chance you're off a little. But what you're doing is you're bringing it in so close that the offness is still on enough. So if you're off by 0.5 percentage point, you might decide that 0.5 percentage point is close enough. It doesn't have to be. Who asked me that question about you can't actually find the probability of being at an exact point on the bell curve, but you can get close left and right of that point? Was that this class or the 243? I don't remember now.
Infinitely close.
Infinitely close, or it's an epsilon delta. It's an epsilon delta. You can get as close as you need to get. So the first graph clearly was not close enough. But now we've gotten so close. Taryn, get that question in 30 seconds, I promise you. I tried to make a 10,000 bar. I tried to make it n equals 10,000, and I think I made Excel full. I didn't think you could pack Excel so full of data that it would fart out. I made it 10,000, I pressed the F9 button, and it went 6.5 minutes later, it went pow! And did one of these graphs. And I was like, sweet! And I was like, they're not going to wait 13 minutes for two repetitions. So I stopped it. I stopped at 100. Go ahead, Taryn.
I think this is something you can base all this off of if you're assuming it's a bell curve.
No, I'm not assuming it's a bell curve. It's becoming a bell curve by itself.
So, like your ADHD thing example, how do you know that that's a bell curve when you're giving it?
Give me 5 minutes tops. 5 minutes tops. See, Taryn's asked a very important question. There are 3 things that this is showing us. 2 of which I think you guys are buying pretty well, correct? You're buying the fact that the bell curves we're getting are roughly centered at the average of the population. You're buying that, correct?
Correct.
You're also buying, I think, that the curves are doing this and this. What you might not be buying is they're doing it in a predictable way, which is pretty slick, actually. The third part that Taryn has verbalized perfectly, by the way, is where does the bell curve come from? Right? You said you're doing all this based on the fact there's a bell curve, right?
When you have enough data, you can see it's a bell curve, but you don't have one.
Define enough.
Well, that's my question. The 105.
Ah, I love that. I love that. 4 is enough. In this case, right? 4 is enough. 4 generates a bell. Ah, I didn't say it was consistent, but the shape begins to appear. It's messy. It's not perfect. It becomes more perfect with more trials, of course. But what is that minimum value when it occurs? It can't be as few as 2 or 3. No. Taryn, the problem is, I can give you a quick and easy answer for one particular set of data. Remember the one I put a formula on the board for? You were asking about a Gallup poll that day. So I had a situation. Gallup poll, it's easy. It's this. This is slightly different because this is an average versus a proportion. It's a different result. It's a different way of attacking it. This is why we base Math 244 around that. You asked essentially the question that Math 244 answers. I hate to be a bastard, but you asked it 2 terms early. And we're slowly discovering pieces of the puzzle. Fair? Maybe fair. Still hate me, that's okay. Well, that's okay, but then you wonder what the hell that piece means, right? No, so here's, speaking of a whole picture of a puzzle, check this out, friends. Here is all of the sheets you just saw in one place. So, check this out. This is the population, this is the set of parameters that we will never know. They're out there in the population, we'll never know them. The average is 8.166666, standard deviation is 2.69-ish. The problem is, we don't know what they are because they're in the population, but as researchers, we want to know what they are, don't we? We want to know what the effect that drug has on the kids, and we want to know also what the plus or minus is of that effect. 10% plus or minus what? Is it plus or minus 10%? Is it plus or minus 2%? I want to know what those are. The best you can do is draw a sample. Now what this graph down here is doing, is it is showing you the same graphs you were just looking at on the previous pages, but all in one place. So every time I press F9, you're getting re-randomized data in those data sets. So you see the bell curve still? We're seeing what Sandy and Taryn and Riley and everybody else was talking about. As the sample sizes go up, front to back, the curves are smushing in and rising up. Look at that guy right there. Boop! That's where it was over 50% for the first time, Sandy, right? So what's happening to the averages of these bell curves? Is the average changing on these bell curves at all?
Standard deviations.
Good. Oh, good. Of the three things, you guys have now nailed two. Number one, the average is staying constant. You can actually see that right here. Those are the averages of all five of those results. 8.12, 8.12, 8.17, 8.1, 8.17. They're all pretty damn close to mu, aren't they? And you can keep randomizing and seeing that. They're bouncing around as we do. And Taryn, this goes back to my point. They bounce. They do. Sometimes they're significantly up or down. And now you're up by 0.25 and so forth and so on. What Alicia just said fascinates me the most. The standard deviation definitely is creeping in. Now that's, the average staying the same is just the curve staying like this. The standard deviation creeping in takes care of two things. It takes care of you guys going like this with your hands, doesn't it? 95%, in other words, is now contained in a smaller place than it was with a smaller sample. As your sample gets larger, the standard deviation gets smaller. So you guys picked that up, right? Watch how it gets smaller. And this is also one of the cornerstones of 244. How is 1.34 related to 2.69? Ish. Ish, half, about half. See, watch those numbers. 1.3, 1.29. They're about half, aren't they? Okay. Ooh, crap, I hit something. I shouldn't have.
Don't do that.
How is 0.89 related to 2.67? Ish.
Divided by 4.
Equals 2.69 divided by that. Here, we'll let Excel do it for us. Whoops. Oh, I'll do it the other way. Hang on a second. Equals G3 divided by 2.69.
It's about 3.
Does you mean G4?
No, G3 right now. I want to copy this down. Okay, so there's about your half, right? That's about half.
Oh, mu.
That's the previous one. That's the previous one. How's this number related to 2.69-ish? I got about vote for about a third. Okay, let's drag that down. Look at that. How's this one related to this one? About a quarter. How's the next one related? Oh, about a fifth, Dylan? He's saying about a fifth? What would that be as a decimal?
0.2.
Oh. What's the next one going to be?
10.
Oh, you didn't fall for my trick. Good for you. A lot of classes say a 6 because it's 2, 3, 4, 5. 10. Why 10? Oh, you're just looking at it. 0.26 versus 2.6 is a 10, right? No magic involved, Sean. No magic involved. Now remember what I mentioned that I tried to make a 10,000 column, right? What would it have been if it was 10,000?
0.01.
Oh, why? That was a lot of phlegm clearing. Sorry. That was a lot of phlegm I just cleared.
I'm a little sick right
Scott said 0.01. Now, how could he have known that if you guys were doing this divided by this, right? To get your values.
Well, it was 10,000.
So what's the relationship between all these numbers? What's varying? that makes them vary? You already know the answer to this.
Standard deviation.
The standard deviation is varying, but what's making the standard deviation vary again?
The sample size.
The sample size. What's the relationship between the sample size and the standard deviation change? How is 4 related to a half? How is 9 related to a third? How is 16 related to a quarter? How is, Corey's got it, how is 25 related to a fifth? Boom! You're seeing it. Think about it. Let's turn Excel off for a second. How do you get, this is one of the, I think this is one of the most interesting results in mathematics.
That makes me feel like an idiot.
How, no! God, no! I'm trying to discover it. No.
I'm saying
When the sample size is 4, the multiplier was a half, right? When the sample size is 9, it's a decrease by a third. When it's 16, it's decreased by a fourth. When it's 25, it's decreased by a fifth. When it's 100, it's decreased by a tenth. What's the relationship between those numbers and those fractions? Boom, Karen, go.
Square root.
Yeah, take the square root of that and make it a fraction. And that's the relationship. Exactly, Faith. That's how I felt the first time I saw it. Shit. But the first time I saw it, a prof just wrote it on the board.
Yep, standard deviation.
They simply said, oh, the standard error of the sampling distribution is sigma divided by root n. And I'm like, why? Why is it root n? And I started futzing. And I said, oh my God, that's cool as shit. So that's why I went to 10,000, right?
Should we put a disclaimer on the video?
Because 10, I'll bleep it out later. Because then 10, that's a market we need to do. Educational videos with like South Park swearing. Yes! Yes! That's what we need. Oh my God, every third
Learn
word.
more.
So why did I go to 10,000? Because what would it have been? 1 over 100, which as Scott just said is 0.01. So I tried to do that, but it was too much for Excel to handle all those calculations at once.
Why'd you go from 100 to 10,000 instead of?
It's a square root, right? The square root of 10,000 is 100. 1 over 100.
And 1,000.
I skipped over 1,000 because 1,000 doesn't have a nice square root. Was anybody wondering when I was going 4, 9, 16? Those are dumb numbers, right?
Not after I saw them.
Not after you saw this. But up to that point, like, why is he using weird numbers like 16 and 25? Those are weird, right? Because I wanted you guys, it's hard to know what the square root of 7 is. But it's easy to know what the square root of 9 is, because of where they live on the number line. So basically, here's the beautiful thing about what you guys just saw. And carry this forth with you if you're taking 244. And leave it stay right here if you're not. That's totally fine. It's totally fine. Statisticians want to study what's called a population. And this is one of the things we learned on the first day of class in here. And we've been developing tools to study that ever since that first day of class. We want to study a population. The problem is, when you have a population, you have no idea what that population is shaped like. It could be a bell curve. It could be, if that's a bell curve. It could be a U-shaped curve, which is called a Weibull distribution. It could be highly skewed. Either right, that's not really high skewed, is it? Right or left. It could be shaped like that. It could be tri or bi or quadmodal. I mean, there's lots of shapes the distribution could have. Lots of shapes it could have. What the result you just saw, which has a name, it's called the central limit theorem. Don't memorize that, it's not important to memorize. That result guarantees us, if you take a sample of size n from that population, so you draw a sample, it's got to be a good sample. It can't be a bogus sample. It can't be like, I'm going to ask you 25. Good, I got a sample size of 25, we're good to go. That's not a very representative sample of my population, whatever that population happens to be. So you take a good, unbiased sample of size n. By the way, 244, one of the first things we do is talk about how to take a good, unbiased sample. It's one of the things we sneak in there. You are guaranteed 3 things. Whatever the population's shape is irrelevant. You know the population has an average, correct? You know it's got an average. This one's going to be right about there, correct? This one, unfortunately, is also going to be right about there because it's symmetric, but it's U-shaped. This one's average is probably going to be somewhere over there. This one's probably somewhat over here. I drew those the same, I apologize.
Yeah.
This one, I'm going to guess it's somewhere right about there. They all have an average, right? The beautiful thing the central limit theorem guarantees, the central limit theorem guarantees. Now, you probably have forgotten this from your quiz on Monday. It was 48 hours ago, it's a long time. Lots happened since then. It snowed since then, it's been freezing rain. that quiz, remember the name of that quiz? In-class quiz, if you like, you don't remember, it's okay. Sampling distributions. It was called sampling distributions. I snuck that by you while you weren't looking, it's okay. Sampling distributions. The distribution of the sample you grab lives in what's called a sampling distribution. Now, believe it or not, you just looked at a whole buttload of these in Excel. Every one of those bell curves you just saw was a sampling distribution for a sample of size 4, or a sample of size 9, or a sample of size 16, or a sample of size 25, or 100, or whatever else, however big it needs to be. Your sample is going to be part of that. So you drew a sample from this population, yes? That sample is going to go down into a curve that will be bell-shaped. That's what Terrence bringing up. How did you know that bell shape is going to be there? He guarantees it'll be. I shouldn't say he. It guarantees it will be there. You will have a bell curve. The results must be bell-shaped. Andre's looking at me going, I don't buy this one bit. That's okay. You don't have to. I proved it on the enrichment page for you. I didn't buy it either. There were 3 things I didn't buy. All 3 of these, basically. All 3 of the results we're about to share again, I didn't buy any of them, so I proved them all for you. It involves some heavy-duty calculus, which I totally, oh, it's okay, you don't have to look at it, you know. But the theorem guarantees us a bell curve. Why does this make us happy? Why does it make me happy?
It's the normal.
Because you know stuff about bell curves. You've just, the normal, exactly, hashtag the normal. Because you just spent 2 weeks studying the bell curve, which means regardless of what the population is shaped like, your sample is going to be bell-shaped. Which means you can apply the results from the normal to the sample you draw.
You got enough of the
Yeah, don't you worry about that. This kicks in at very small numbers, Terry. Very small numbers. And we have corrections for when they're not. If they're not big enough, quote unquote. Don't worry. It's all taken care of. And it's taken care of within the theorem. Number 1, the average of this distribution is going to be mu. The average is going to be mu. We just saw that, didn't we? Mu, although it's going to be unknown, is right in the middle of that sampling distribution. It's right in the middle, isn't it? That's a beautiful thing. The problem is, there's only one small problem. And the small problem is that that's great if your sample average actually lands on that bar, right? But what if it lands off to the side a little bit? Which it most likely will, correct? It's not going to land directly on the middle. It's most likely going to land one side or the other, right? Well, why is that okay?
Standard deviation.
Because the standard deviation is shrinking the larger your sample is. When you got a small sample, all you got to do is allow for a large, what's called standard error, which is the standard deviation of this curve. Statisticians and researchers make up new names sometimes for what they shouldn't. The standard deviation of this curve is called a standard error. Now, I don't know why it's called that, it just is. And we'll talk about that in the beginning of 244 quite a bit, because it's tied to the margin of error. It's directly tied to the margin of error. So this thing's standard deviation, the sampling distribution's standard deviation is actually called the standard error, which is usually called SE in research journals. You've probably even seen it. Alicia's like, yeah, I've seen that before. It's called SE. Its formula is going to be sigma over root n. That's the root n you guys just went, oh, I see it now. That's what you saw. You saw it being decreased by a factor of root n. So Terran, you can see how a small sample will be dealt with. It'll be dealt with because the standard error will be larger with a small sample and smaller with a large sample.
I guess I don't like a lot of error is my issue.
Oh, sister, good for you. Because there are different kinds of error. There are false positives, there are false negatives. You just studied those, didn't you? But there's also the natural flip-flop of a sample that you have to be okay with. So if you don't want a whole lot of error, then you go get more samples. But sometimes you can't. Suppose you're doing something like you're testing airbags in Lamborghini Countaches. You know, a car that costs 6 figures, right? Let's go smash another few into the wall. You know, Guido over here is going, no! Right? So you can only smash 10. We have a whole part of 244 devoted to the Guinness Brewery, who dealt with this same thing 100 plus years ago. William Gossett at the Guinness Brewery had the same question. I don't like a lot of error, but I also can't get any more samples than I got, because at that point, Guinness was a tiny microbrew. So what did he do? He came up with another distribution like the bell curve, called the T distribution, or the standard, or the student's T distribution. that does the same thing on small sample sizes. Everything gets dealt with, but the thing is, I want you to understand the Z curve really well before jumping into the T curve. Does that make sense? Good, sister, good, good, good. So this is, I think, the most important part, next to the fact that it's a bell curve. The bell curve makes me very happy because we have still normal, we have ways to deal with bell curves, we have tools. The fact that the average is at the height makes me pass out with happiness. Honestly. And the fact that the error shrinks as the samples grow, that's why I have to just ask for a check and go home. Because it's wonderful. It's absolutely wonderful. This is why bell curves materialize in so many places. It's not because it's luck or it's random chance. It's because they have to. It's because they have to. Bell curves are prodigious because of this fact. As long as you sample well, and you sample arguably independently, like we do the binomial, this is going to happen. This was kind of badass about it. Beep. Yes?
I'm going to take a leap out here.
Go!
So bear with me.
Yes.
So I took a business finance class that I've already done my rant about how we should be taking this class before that.
So true in a lot of ways, yeah.
Because for a business degree, all you need is Math 60.
For your AAS degree, yes? Yes, correct.
Which is a disservice across so many, anything.
We're dealing with that, but go ahead, Joanne.
Yeah. So as I'm sitting here,
May I interrupt for a second? Did you take Math 31?
no.
You probably didn't. We created an alternate Math 20 called Math 31, which is like Math 20 and 243 mashed together.
Did you do that like in the last year?
It's about a year and a half ago.
Yeah, I already.
You had already taken it, so I apologize. I always hate saying this, but I apologize being late for the student who's gone through it already, but we patched that hole, I think.
Right, but I'm just looking at this, and with all of the reports that we were looking at,
Yes.
and all the numbers, and I'm just taking this into that situation about, and Taryn's point is, you're a great person for a business because you are looking for less error, and you want the big, pot that's good, and that, you're making enough money, here's the little bit, and the things that are not producing well are going to show out.
Oh.
Are going to show.
As long as you're looking for them.
Right, which is what you're looking for the error. It's, they're going to show up as long as you're looking.
As long as you're paying attention. It's interesting you bring this up, because on your exam you're doing for next week, there's one problem where you actually microanalyze a distribution and you see which chunk of the average comes from which category. You do exactly what you're describing. When you look at the student debt problem, when you revisit the student debt problem in the second part, I go in there and I say, look at each category of debt and how much of the average is being contributed by each category. You often hear about people that owe $200,000 of debt to the overall average and blah, blah, blah. We should be looking at the people that have $10,000 and $15,000 of debt because they're the ones that are contributing the largest percentage of the average. But we don't talk about them in the news. We talk about the photographer who had to borrow $250,000 to get a degree that you no longer can work for because the economy has collapsed. So you're going to do a problem that's related exactly to what you're describing and talking about with Taryn's like micro-analysis of that. It's very, very important. It's a very, very good point. What blows my mind is, and this is why I'm sad that you had to suffer through Math 60 unnecessarily, Math 60 is a great course, but not for this. What you're talking about right now, this is not the right thing for Math 60. Math 31 actually gets into this on a more macro level, so I do apologize that you missed that option. I know,
and moved ahead. But it's good to know. I mean, it's good to know.
We're dealing with that.
That situation because we, as a class, and I'm talking with the high percent.
Oh, for sure.
All the group that I'm meeting with are expecting A's and nothing less, which is great. But I'm like,
it's always so adorable.
I know.
Are you guys learning? What?
Right? Yeah. But
Don't worry about that.
Over head.
That's the problem. And I've heard the same thing from forestry. I've heard the same thing from HHP. I've heard the same thing from physics. This course could be a prereq for so many other courses because of that, because data is becoming part of our conversation. You guys use Google, I'm assuming daily, at least daily? How does Google run?
I didn't just use it.
How does Google run? On frickin' data. I mean, it's data analysis. How does anything you use handheld work? data. It's all about how to compartmentalize and analyze data, whether it's continuous in 251, whether it's discrete or continuous here, it's all data. So Taryn, back to your question about larger sample sizes, this is why I had you do that project, number 3, the Monte Carlo project. You want more trials? Go get them. Simulate it and run more trials. That knocks your error down. Essentially, think about it mathematically. You see that root n right there? Huh? You make n big enough. Sorry. I just lost it, didn't I? You make n big enough, what will this shrink to? This is a little bit calculus driven. You make n big enough, n gets infinite, right? So you've got some fixed number, like 2 or 3, over infinity, which is essentially what? 0. You can make it as small as you need it to be, Taryn. If you want to be off by no more than 0.2% or 2% or 20%, you can adjust the n to do that. If you want to make sure that your pill for headaches is relieving pain by at least 2 marks on a pain scale, you can do that. 244 is doing a project due tomorrow that attacks just that question. It all depends, though, what parameter are you trying to shift? Because it does vary, because some are discrete and some are continuous, and you can't do the exact same math on both. But the reason your question is so awesome and it's frustrating to you is you essentially asked, Sean, explain 244 in 5 minutes. And you just can't, right? I can tease out bits and pieces of it through the term when it shows up. You just got a big piece. This is a huge piece of 244. Now, those of you not doing 244, have fun with it. but realize the question Taryn asks is always a good one. Where'd you get your data? Can I see? Did you guys hear this one? A study was done in Chicago. I just saw it was on NPR 2 days ago, or yesterday. A study was done in Chicago that people who talk on their commute to strangers have a more pleasant experience commuting than those who don't. So the idea was you get on a subway, which I know Ben will never have, unfortunately, but you get on a subway or an Amtrak train, light rail, and you get in there and people just sit down, and nowadays the earbuds go and we put our head down. But the experimenter wanted to see, I wonder if it will be any different if instead of just walking in and putting the earbuds in and going down, we engaged conversation with the person next to us. And they had a couple levels of conversation. One was completely ignore. That's one. One was engage in pleasant conversation, quote unquote. I don't know what that was and I can't get the abstract to find out. And the third was treat them like you would quote unquote normally do on a commute. And I don't know what that means either. So I questioned the methodology because I'm a fairly gregarious person to the point of annoying introverts. Like I'll get in like, how you doing? And then people are just like, and I don't want to piss people off, so I kind of back a little bit off on that. The results, though, unfortunately, I start asking questions immediately. I'm like, wait, when you say you had a more pleasant commuting experience, how did you measure a more pleasant? Guess how they did it?
Because you didn't have to talk to anyone.
Guess how they gave him a questionnaire at the end. Say that again, Andre. They gave him a scale, 0, very unpleasant, 10, very pleasant, and they said, go in here and circle the number. As a statistician, that makes my blood boil. That's called a Likert scale. And Likert scales are good for many things. They are good for many things. They are absolutely garbage, in my opinion, for taking an average of. Because you have taken qualitative data and assigned numerical values to qualitative data without any coaching. Exactly! Mike Wright! Of course, it doesn't apply to you guys because you don't have to do them because I didn't wait it too long to get them linked up. But so Taryn's question does not fall on deaf ears, right? Always question any study you hear about. Go find the raw data. And don't be satisfied until you have. Right? If you're ever concerned about a sample size being too small in a particular study, just email me. I'll run the numbers for you. Study to study, I can figure it out for you, not a problem. I hope you do. I hope you do. Send me, hey, I got this Gallup poll, it's 1,500. I'm like, what's the margin of error? 3%, it's fine. Or, hey, here's a Gallup poll, it's 800. What's the margin of error? 4%. That's fine. But if they want 3% with 800, that's not fine. And then in the situations, I can explain to you why or why not. I just can't give you a blanket answer for all of them. Fair? I feel terrible because it feels like I've been pushing back our questions for 15 weeks now, but hopefully I've been giving you enough little snippets here and there as we go. And it's all we've been learning as we go. Davidson, go ahead, give a question, my friend.
Oh, no.
No, you're just stretching. I just interrupted it. Scott.
Well, off of that, I know that they have. I took Mind in Society, Psychology, Mind in Society, and they do have a way of calculating out whether like you're one of the extremists, which is like I hated it, and got 1, and then I loved it, got 10, and you count up the amount of 1s that you have, and the amount of 2s you have, and the amount of 3s you have.
Hear what you just said? you count up this and this and this. You're going for more of a mode, right?
Well, essentially, yeah. You're hitting the mode of like, okay, they're typically really extremists or they're really like narrow.
But you're measuring it correctly, you see. When I look at a course evaluation histogram, which I always get when I get them done out, there's in a class of 30. Say again.
Did you submit it so it's online yet?
I can't. I missed the damn submission box. That's why I'm gonna have you guys do it in class on Monday. Anonymous, of course. I mean, I'll leave the room if you want me to. Totally fine. But yeah, I missed the checkbox back in week 2, which nobody told me about. So anyway, I get that histogram back. And what a lot of people do, I actually heard a colleague years ago tell me, this is back when we used 0 to 7 scales or 1 to 7, as long as you average 7 on your course evals, everything will be fine. Like, you do realize that to average 7 on a 7-point scale, you have to get all 7s. Huh? Really? Like, seriously? You're saying everything's gonna be fine. Drink the Kool-Aid. It's like they're making this statement. As long as you average 7. I mean, because Scott, what happens is I always piss at least one person off.
Yeah.
It's just a fact of life. Somebody can't deal with my class, and that's okay. Because I'm not saying I'm the best fit for every single person. But am I the best fit for the modal person in this room? That's a different person than the average person in this room. Modal is based on counts in a category. You can get a mode of 7 very easily. Just have the most 7s and fewer of everything else. But averaging 7 is damn near impossible for anybody. Does that make sense? What you just described is a proper way of dealing with Likert scales.
Yeah.
But who does that?
Well, and it's like, again, this was just a mind and society
Oh,
class.
brother, I'm glad you're learning that. Sorry, rant over. Alicia, you hit a nerve right there, girl.
I'm sorry.
No, it's good. It's good that you heard that because I've had PhD students come in with Likert data. I want to prove something. I'm like, okay, first of all, number one,
Let's
sit
not
down.
use that.
Let's make some coffee. You can't prove anything. Can we support a hypothesis? Maybe. I want to do an average. Sit down, another cup of coffee and a biscotti. Here's how we're going to do it without averages. And by the time they're done, they're like, oh, this is really cool. It's actually easier than I was trying to do. That's because you were trying to fix the hole in the wall by blowing the whole wall out and building one made of Legos. When all you had to do was get a little spackle.
Legos great.
Legos are great. I'm not saying they're not. Please, Sandy.
Maybe some of the information is modal or like that, but they're using average because people don't know what modal
It-
means.
Because if I heard the modal of blah, 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 I'd be like, all right, whatever, but the average
May I
is
get
something.
244 on you just for a second?
That's fine.
You watch it back there. The problem is, you are, and this is the same problem I have with answering Taryn's question generally.
Oh, okay.
Every sample statistic has a way of expressing the error around that statistic. But they vary with every statistic. Some are biased and some are unbiased estimators, as they're called. Average is what's called an unbiased estimator, which means, and you saw it right here.
Because you're taking everything.
Right, and on average, it targets the bell, right?
Yeah.
On average, it's a very specific average. That's the add them up and divide by how many there are. The median doesn't do that. The mode doesn't do that. The range doesn't do that because it varies too much. So what you have to do is build a different plus or minus around those. I'm not saying you can't. I'm saying the default methodology for most people is not to look at the other ways and just go straight to what's called a t-test or a z-test and put a plus or minus based on that on there. And I'm saying, wait a minute, you shouldn't be doing that. It goes back to the whole, my head's in the oven, my feet are in the fridge, on average I'm fine. Oversimplifying an average, right? Oversimplifying an average, that's the problem. That's the problem. Davida, go ahead.
No, I just had a question
Yeah,
on the
please.
graph back on. So if I want to make sure I understood that. So you were saying that by increasing the number of samples,
Of sample size, this
we're always
shrinks.
going to end up with a bell curve?
Oh, the bell curve happens almost immediately within the first couple, 3 samples. Sample size 3, sample size 4, the bell pops up. For years, it's funny you mentioned 30 before, Randall. For years, the number 30 was used. I just quoted with 3 fingers. The number 30 was used for years as a minimum sample size. But it's funny now, if you look at different textbooks, they say, well, if the data isn't too skewed, you can use 24. I'm like, well, how do you know if the data is skewed? It's in the population. So I just say, throw all those rules out. The bell curve shows up almost immediately. It might be a noisy bell curve at first, until you get enough to see what's going on. The bell curve will happen almost immediately. It becomes more bell-like with the larger samples that you get. So if you can default to more of larger sample size, you're going to get more precise data. You're going to get more precise data. If you will, think about it like shooting a gun. The central limit theorem guarantees that if the target is that switch plate over there, the central limit theorem guarantees that on average you're going to hit the plate. The problem is, with a sample size of say 4, that average might look like this. with a sample of size 100, it might look like this. See the difference?
Uh-huh.
Fair?
Yeah,
Does that make sense? So the precision, so the average gets more precise. The estimate gets more precise with a larger sample, which causes the bells pulling in and rising up. Fair.
Cool. No.
That's good. That's good. Joanne, go ahead.
So I can see how Aaron kind of, and I don't want to but I won't put words in your mouth, but because you get the small, or the bigger the sample size, the smaller the data, or
The smaller,
more,
the tighter the curve. So it's tighter and taller.
So it's hard to say, okay, if I'm going to look at something and the curve is stretched out.
You must have a small sample.
Right, small, right.
Right.
Right. But then how can that and then a larger sample be so connected? You know, like, and so
That's the go-between. That's the key. So go ahead, Michelle.
It's like a microscopic view of
It really is, and you can make a tight curve look stretched out if you zoom in on it close enough. But I think Joanne's saying, assuming this is 1 and this is 10, a sample of size 4 is going to be wide and short. A sample of size 40 is going to be 1/40th taller, whatever. So the connection is that's the rule that connects it all together. That's what's so, and that's why I said we could have used any of the other 4 colors of dice too, and you would have seen bell curves appear. And those bell curves would have kept getting tighter and taller, but their centers would have been at their particular averages. They wouldn't have been at 8.16666. They would have been at 4.5 or at 7. Exactly. They chase the population average. They give you what this is essentially is a pair of eyeglasses that lets you look at the population indirectly. Kind of like the ones my son built out of a couple rolls of hand towels. He built like this cool mirror thing where he can look around the corner. That's what this does. It allows you to look at a population indirectly, but still get something from it meaningful. Sure, there's error. The only way to eliminate error is to do what? To eliminate error.
You'd have to sample.
You have to sample the whole population, which becomes a census. If we could do censuses with any regularity, you would not be sitting here in 243, nor in 244, nor in 105. Because that's not statistics, that's parameters. The course isn't called parameters, it's called statistics. Right? No, you're not! No, you're not! Because you would have still... I'm going to stop talking about it. Problem solved. Oh, my money back rule. So we have to make peace with error. Thank you, Terry. I saw another hand go up my thought. Scott, go ahead.
I was just going to say, like, you know, so on a manufacturing note for 10,000.
Yes!
What is, because like, you know, if we have several manufacturing companies working on a similar product, how can we find where the error is occurring from all those manufacturers?
Ask yourself what tolerance you will accept.
Well, this is usually the highest tolerance that they'll do, because I know.
No, but you have to give me a measurement, like how off. Suppose you're making a ball bearing.
Well, so.
Go with this for a second. Go with this for a second. You're making a ball bearing.
Yeah.
How off can that ball? Suppose it's supposed to average. How far is that? A third of a centimeter. Let's make it one. Let's make it easy. A big ball bearing. 1 centimeter. How off will you allow yourself to be from 1 centimeter? Make up a number.
Like 2 centimeters.
2 centimeters. That's a nice wide margin. So over here, Scotty, what you're saying is that no, don't you worry about it. 1 centimeter plus or minus 2 centimeters, right? Okay, so that's 2, that's 3, here's 0, here's -1. I know that doesn't make any sense mathematically, or it doesn't make any sense realistically, mathematically it does. You can now set up this curve so that it traps 95% of your data between those 2 numerical values, and that will tell you how large a sample you have to do to get it. That's one of your answers in 244, Tara, right there. Basically, that reverse engineering the sample size from that.
My issue is that, like, I remember a while back when we had cortisol injection shots, and they were like, they had a bacteria contaminant. They got into the cortisol.
That's a different story, brother.
But it's just like, it's treated just the same way as manufacturing. So it was just like
Oh,
the
God,
amount.
really?
That's why they recalled all of them. They didn't know.
Oh, okay. So the bacterial infection has nothing to do with statistics.
No, but it's just the fact that
The recall.
the recall on
Yes.
that product, because they couldn't figure out where it would come from, because the probability is that we had no idea.
Correct. May I jump in?
Zero, one.
May I jump in?
Yeah, go ahead.
I guarantee if they can figure out what the batch numbers were for that batch that they think was
what I was
contaminated,
wondering.
they recalled every single one. Why? It goes back to your project you guys just turned in. What would they rather have in a case like this, where you've got an injection of a drug that somebody needs to get, right? And somebody's going to put it in. It either may or may not be contaminated. What kind of error would they rather have in case the error exists? A false positive or a false negative?
False positive. Negative.
Definitely a false positive, because they want to deathly avoid a false negative. You want to avoid a false negative would be, go ahead, keep injecting, it's fine, and the bacteria is actually in there. That's a false negative, right? Let's go through the table. A true positive means recall the tube and there's actually bacteria in there. That's a positive test result, and it's a true positive because the bacteria was actually there. Is that fair?
I thought you meant like positive.
That's okay, that's okay, that's okay. No, I'm talking mathematically positive. A true negative would be, go ahead and use it, and it's actually fine. And it's actually fine. So that's a true negative. Negative test meaning we didn't identify bacteria. True negative meaning it actually wasn't any bacteria in there. A false positive would be, give me that tube. It's actually fine. But I'm playing it safe by taking the tube away from you and making sure we give you one that we know is clean. A false negative, though, is, here, go ahead, but it's got bacteria in it. They want to deathly avoid that, don't they? Why? Give me one reason.
Well,
I was thinking for the overall health of the population, but yes, lawsuits are probably from business endpoint a much more realistic exercise, right? So, of course, but the lawsuit will definitely follow immediately. I told you about the Ford Pinto, right?